Good afternoon, all. It's my great pleasure to introduce Professor Anthony Didlake, and professor at the Pennsylvania State University in 2016. Professor Didlake, who earned a BS in Geology and Geophysics from Yale University and his graduate degrees, Master's and PhD at the University of Washington, has research interests at the intersection of cloud dynamics and microphysics and topics spanning tropical radar and mesoscale meteorology. His principal research focuses on the use of radar, land-based, airborne, and spaceborne, I guess you could also call those extraterrestrial radars, and numerical models to understand the dynamics of tropical cyclones. This research explores tropical cyclone formation, changes in intensity and structure, environmental interactions. Additionally, his interests also include mesoscale precipitation processes and Doppler radar retrieval techniques. As many of us on this that are participating in today's virtual colloquium, we can track our first recognition of an interest in our science from a seminal weather event. For Professor Didlake, a native of Michigan, his passion for atmospheric sciences was sparked by Hurricane Andrew. We're looking forward to your talk today, and the talk with the title of Asymmetric Aspects of the Secondary Eyewall Formation in Tropical Cyclones. Welcome, Anthony.
All right, thanks, Michael, for the introduction and the invitation. I'm excited to be sharing my work with everyone here. Of course, I'm very familiar with the department and know many of you, and I'm happy to have chatted with a few of you and met a few of you as well. Yeah, I started being interested in hurricanes even though I was growing up in Michigan. But it's one of those things where I was happy that I was away from it, and I'm going to try to keep clear of tropical cyclones if I'm not flying in them. I'd rather fly into them. All right, so let me share screen. All right, can you all see my screen?
Yes.
It looks good.
Okay. All right, so the work I'll be presenting today has been a joint effort with my grad student, Chao Lam Yu, former grad student. He's now a postdoc at University at Albany. Also, people from NOAA HRD have contributed to this work: Rob Rogers, Paul Reeser, Win-Chao Lee from NCAR, Rob Nystrom, who's a former student at Penn State, now at NCAR, and the late Fuqing Zhang. So let's see, I'll be diving right into secondary eyewall formation and eyewall replacement cycles. So here we have a radar loop of Hurricane Irma from 2017 from the land-based radar as it went north of Puerto Rico. And one thing that I wanted to point out are the major features are the eye and the eyewall of the storm. Those are jump out at you. But in this loop, you also see the formation of the secondary eyewall that first started off as a lot of this rainband activity that eventually became more organized, going from a spiral into a more quasi-circular feature. And this is one of the, I guess in the past 5 years, we've had eyewall replacement cycles or secondary eyewalls form within view of these radars much more frequently given the landfalling storms. And it's been a boon for getting a lot of great observations of not just hurricanes, but this specific process. So eyewall replacement cycles are an intercore process that pose a unique and scientific and forecasting problem that involves, let me do this, laser pointer. It involves intensity and structural changes. So here is evolution of a modeling simulation from Rosoff et al. 2012. Here you can see over time, a lot of these spiral rainbands eventually coalesced into a secondary eyewall. And eventually this inner eyewall was cut off from its source of high theta E air and the outer eyewall became the primary eyewall of the storm and basically took over, and that's the eyewall replacement. So this eyewall replacement cycle, they typically begin with an expansion of the vortex circulation, which you can't see in this reflectivity field, but usually we do see an expansion of the tangential wind field that coincides with an increase in the outer rainband convection. And this rainband convection eventually coalesces into a secondary or outer eyewall that also has a tangential wind maximum. And this stage of the eyewall replacement cycle, the very beginning stage, is what we call secondary eyewall formation. And it's several theories have been proposed for physical processes that are most important for causing a secondary eyewall. But there is no consolidated theory as of now. But as I said, it's been an active research area for the past couple of decades. And some of the prominent theories include wave mean flow interactions that involve vortex-Rossby waves. Also, the upscale interaction of convectively generated PV anomalies in the form of these spiral rainbands, which I will be talking about in depth today. There's also what happens with the boundary layer. And so there you can have a boundary layer interactions via a feedback through balance dynamics, or convection that comes about through unbalanced dynamics, unbalanced in the sense of gradient wind and not balanced in the momentum equation. So with all of these theories, many of them focus on axisymmetric dynamics that occur when rainband convection sufficiently populates the outer region. Here we have a schematic of the reflectivity structure of a sheared storm, where you have the eyewall near the center and the overall rainband complex that can form when you have a shear. Now, these rainbands, unlike are very important for axisymmetric dynamics, because although they are asymmetric features, they are important for sparking the initial axisymmetric signal that a lot of these theories rely on. But rainbands themselves are asymmetric features that have their own organization and processes that occur on a range of scales, from convective scale to mesoscale. So it's important to look closely into these because their exact role, although seemingly very primary and seemingly very important in the evolution from an observational point of view, their exact role in secondary eyewall formation is not fully understood. So that's part of one of the driving forces of my current research, is answering these questions of what are the rainband structures and dynamics that are important in the earliest stages of secondary eyewall formation. And I'm also interested in knowing what conditions create these specific rainband patterns. So I alluded to this earlier, that when you have deep layer environmental wind shear, so if you can have a 200 to 850 millibar shear vector that is pointed northward here, you can have a rainband complex that begins to organize. It was termed the stationary band complex by Willoughby et al. in 1984. And in this organization, what we get is a organization of the precipitation regime that aligns with the wind shear vector. So when we look to the right of shear, we have the beginnings of new convection or convective precipitation that form these isolated or connected bands, and they propagate around the storm to display the life cycle of convection, where eventually they collapse and fall out as stratiform precipitation in the left of shear region. Generally, this is the part of the storm that you can have some very active convection here, but it's predominantly on the mesoscale level, you have a pretty strong stratiform precipitation. And because this is happening on mesoscale rather than a convective scale on the other side of the storm, these features can project strongly onto the axisymmetric storm structure. So if we took an azimuthal average, this part of the storm, whether that be heating or tangential wind anomalies, they project strongly onto the wave number 0 structure or axisymmetric structure. And that's what ultimately is the most important driver of the storm evolution. Specifically in the stratiform regions, modeling studies have shown that this part of the storm is very important in secondary eyewall formation. Many of these studies isolate this part of the storm to show what specific physical role is causing the entire storm to evolve into a secondary eyewall feature. For example, these diagrams were shown in Fang and Zhang et al. 2017. And what we have here is an axisymmetric structure of the showing wall PV and the outer rainband PV that can show up if you have enough rainband precipitation. And when you have this upper level PV, that's largely due to the stratiform nature of the precipitation. And because they're so large, they can project pretty strongly onto this axisymmetric structure. And this mid-level updraft that forms is a response to the expansion of the wind field over time. So here you have the wind field at time 1 that eventually expands as a result of, or in combination with, this outer rainband feature. So eventually, one of their hypotheses was that this wind field, this expanded wind field creates a vorticity gradient and a vorticity perturbation in the low levels that couples with the boundary layer and helps to induce an updraft. And what they hypothesized was that this mid-level feature develops downward and meets the boundary layer updraft and causes a secondary eyewall. And this is what we call the top-down approach to secondary eyewall formation. Now, the downward development is definitely one aspect that I will be focusing on here in this talk. So,
if you look at the bottom of your screen where it says that you're sharing your screen, you can click on hide to get rid of that box.
Oh, thank you. I thought that was something that only I saw.
Yep, on the far right. There you go. Sorry to interrupt.
No, thank you. Good, now I can see it too. I know with Zoom, it's one of those things that you can't get rid of. So it's nice to get rid of that. Okay, so these modeling studies included Fang and Zhang et al. 2017. And what I'm going to show here is a combination of observations and modeling studies, both idealized and real case simulation that focuses on the stratiform precipitation, specifically this downward development of the rainband complex and how that can play a role in secondary eyewall formation. Now, when we go through these studies, I'll be using the lingo that we use in the shear TC world, where we have 4 quadrants: our downshear left quadrant, upshear left quadrant, upshear right quadrant, and downshear right quadrant. And it's nice to think about these quadrants as an evolution of the rainband complex, starting from the upshear right, where they typically begin, and end in the upshear left. All right, so from my paper, Didlake et al. 2018, I looked at secondary eyewall formation in Hurricane Earl in 2010. Here we have microwave satellite imagery, about 12 hours apart over the course of a couple of days. Where we also showed this on August 29th. You can see that it was a weak hurricane that over time became stronger and more organized and started to develop an even more clear rainband complex. And that was much more prominent at 12:26 on 8:30 here. 12 hours later, you can see that there was a clear concentric eyewall structure. And so I'm interested in seeing how this rainband complex organized itself and evolved into this circular feature here. One thing to note is that the shear direction changed over time, but the complex stayed aligned largely with the shear vector in the way that we hypothesized from previous studies. So the thing about Hurricane Earl, if many of you remember, we had like 3 different field projects going into that were occurring at this time, and so there were many planes that flew in and out of Earl. And one of those, or a couple of those were the tail Doppler radar, or the P3, NOAA P3 planes that had the tail Doppler radar. And so we were able to capture a good analysis of the wind structure at about these times, 12 hours apart over the course of the 2 days. And so here we have the axisymmetric wind, tangential wind in the colors, and our reflectivity in the black contours for these 4 flights that were, again, about 12 hours apart. So at first we had a developing eyewall over time. And you can see this storm by flight 2 had produced a more organized eyewall at a much lower radius of maximum wind. These gray dots are indicating the location of the radius of local maxima in the axisymmetric tangential wind. And of course, we have here showing the primary maximum of the primary eyewall. You can see over time the storm intensified even more. This was a rapid intensification phase of Earl. And I want you to take note of not necessarily the eyewall that's strengthening, but what's happening in the larger radii, so outside of 75 kilometers. You can see even up through flight 4, there's just strong acceleration or intensification of the tangential wind. And at about flight 4, you start to see the hints of a developing secondary eyewall. Here we have the radial and vertical velocity that show the same, the corresponding secondary circulation. So here we have in flight 3, strong inflow, updraft, and outflow, showing the eyewall here. And then as we get to flight 4, you can again see at this location of a developing secondary eyewall, we have strong inflow, updrafts, and outflow that correspond to that secondary circulation at that location. So this is the axisymmetric structure of the radial and vertical velocity and tangential velocity. Now, what I wanted to do was focus on because I had several flights, and each of these flights had at least 3 overpasses, 3 passes through the center of the storm. I looked at them individually, specifically in a shear relative sense, to see specifically happening in the downshear left quadrant. The downshear left quadrant is the first quadrant where we had our stratiform precipitation. And in this region, you can see again, the colors are the radial flow and the contours are the vertical velocity. Black is updrafts and gray dashed are downdrafts. So at about a cross section right here, within the downshear left quadrant, this is the tail Doppler. I'm sorry, this is the lower fuselage radar reflectivity. In this region of heavy precipitation, you can see this clear mid-level radial inflow that is also descending up until you get to 125 kilometers radius. And this mid-level descending inflow was a mesoscale feature that was all throughout the downshear left quadrant as noted by this average. I'm sorry, this isn't a cross-section for this. This is the overall average. And the other prominent thing here you can see, this is the eyewall, and this is another deep convective feature. But just at the end of this mid-level descending inflow, you have this deep updraft that's emanating from the boundary layer. And that was on flight 2. Now, about 12 hours later, in flight 3, which you see still in the downshear left quadrant, is a very still less clear mid-level descending inflow that is going all the way to the boundary layer. And there's even some enhanced low-level inflow that's associated with it. And part of this average, there were locations of deeper, stronger updrafts, but the average, you still see some hint of an updraft at the end of this descending inflow. So this was, is that a hand?
Anthony, it's John Martin here. I got a question. I wonder if, is the interpretation compromised somewhat by the fact that the shear vector is not perpendicular to the cross section in the second case?
That the shear vector, okay, so one thing So the answer to your question is no. But
Okay.
another thing is that these are actually averages of the entire quadrants, not this black cross section. So I
Oh, okay.
my paper.
Sorry.
So you can see these gray dots as being the shear quadrant. These are the shear quadrant separations, and so you can think about this as this is the average over this entire 90-degree swath.
Okay, thank you.
All right, so that's the hand raise noise. Good to know. All right, so this is a very interesting feature. It clearly happens over the course of many hours, and it's also over the course of a mesoscale structure. And it was very much reminiscent of something I had studied before, which is the overall structure of a mesoscale convective system with a leading convective line and a trailing stratiform region. So here in this diagram, or in this conceptual model, we have a clear inflow that goes into the convective line. And then behind the convective line, you have ascending front to rear flow within the stratiform cloud, which creates a horizontal gradient in buoyancy. And that also creates a meso low in the mid levels. And that with that meso low, you have air that's being drawn in from the environment within the descending rear flow. And that descending rear flow is, of course, accelerated by the stratiform, or by the sublimational, melting, and evaporative cooling. So how does that relate to what we're seeing here? So this would be, if we took this radial cross-section and directly correlated it with what we see in this, conceptual model, then we would think that we have a flow that's feeding into the convective line from radially inside of this stratiform region, just out beyond this convective line. And again, we're in the stratiform dominant region of the overall rainband complex. But we know that that's not really happening here. There isn't a very clear, there is inflow here, or I'm sorry, this is radial inflow that's going this direction. So this is not what's happening here in the low levels. In fact, the feeding into this convective line is actually coming from upwind rather than radially inside. So you can think of this, the relationship to this conceptual model, if you just bend it and think about the inflow coming from upwind, also where we have our dominant convective regions of the rainband complex. But the same physical processes are working for this stratiform flow and driving this mid-level descending inflow in the same way that we have a descending rear flow in the MCS. And this wasn't the first time that I saw this. I saw it in Hurricane Rita in the stratiform rainband region in 2005, right before Rita created a secondary eyewall. This clear descending inflow, I called it the mesoscale descending inflow, or MDI for short, just showing the same features, and we even see more enhanced boundary layer inflow here. All right, so I saw this feature. What does it do? What role does it play in the storm? In order to look at this, I did a tangential wind budget analysis. So here we have a tangential wind equation, budget equation, and focusing on the radial advection terms and the vertical advection terms. And what I did was calculated these two terms over all four quadrants and also the total. And you can see at for flight 2, in this region where the MDI is occurring, the downshear left, this purple line, is showing or suggesting that we have more tangential wind acceleration due to this mesoscale radial inflow. When we have this mesoscale radial inflow, it is advecting high angular momentum air inward, and that helps, or that leads to an acceleration of the tangential wind. And that's largely occurring most prominently in the downshear left quadrant. And it's helping for the total storm to increase its wind field in these outer regions. And that's helping to broaden the overall wind field, which is what we saw in the axisymmetric storm. 12 hours later, the downshear right quadrant in the blue line here becomes also a significant contributor to accelerating the outer regions here. But the downshear left is still there, helping to accelerate the local winds from these two terms. The other terms are not as significant in shaping the radial cross section. They're not as significant in shaping the secondary circulation flow from an axisymmetric sense. Now, these were the instantaneous calculations of the budget, and when we compare it to what actually happened and the change in the tangential wind, you see that in the downshear left, there actually was a clear increase in the tangential wind. And then our top two quadrants overall were the downshear right and downshear left, and when you go from flight 4 to minus flight 3. So these budget equations corresponded pretty well to what actually happened. Now, why was all of this important? It's because at these radii, where you have this strong acceleration outside of the eyewall itself, this is actually about the location where we saw the developing secondary wind maximum in the low levels. And this is, of course, a developing secondary wind maximum associated with the developing secondary eyewall. And you can see that in the overturning as well. So this is what I showed earlier. So the takeaway was that this MDI is very much connected to a local acceleration of the overall wind field. And it's also helping to accelerate the winds through radial influx of angular momentum. And there's an associated convective updraft that is also accelerating the winds right here. And it seemed to be very much connected to this secondary eyewall that eventually developed in Earl. And I created a hypothesis for why that would be. And I actually got to, the other thing about this was that the downshear left quadrant had the strongest secondary tangential wind max. So I created a hypothesis for why this would be, and I'll talk about it a little bit more when I start going into a lot of the modeling work that my student Zhang Yu was able to do. So downshear left quadrant, stratiform, mesoscale descending inflow is going to be the prominent theme here and how it connects to secondary eyewall formation. But let's look at how we can examine this from idealized simulations. What Zhang Yu was able to do, I call him Chris, he goes by Chris. He revisited, if anyone knows the Moon and Nolan 2010 paper, what they did was they took a vortex, an idealized vortex, and tried to simulate the heating structure of different parts of a rainband complex. And they showed different circulation patterns that appeared pretty similar to those that are observed, and tried to get a sense of what role or how the overall tangential wind field changes. And so I wanted to piggyback off of that. And so what we did was we took a WRF simulation with 1 kilometer interdomain resolution, and we got rid of all of our parameterizations and moisture, just so that we can look at a vortex as the only response to different heating regions. And so we created a idealized stratiform region of heating above the melting level and cooling below the melting level. And we plopped that into the initial vortex, which had a wind profile shown here. This is the vertical and this is the radius. And this was how we dispersed this heating and cooling structure so that it had a spiral nature like a rainband complex would. And we let it go, we let it run and tried to look at what this response was. So in the plan view, at about 4 kilometers or 3.6 kilometers, in this location is where we had our heating cooling structure. You can see that there is still cooling I'm sorry, this is vertical velocity. There is a clear downward motion in this cooling region, which we expect because it's negatively buoyant. And that agreed pretty well with the Moon and Nolan simulation. But if you go a little lower in the atmosphere, so at about 2 kilometers, we start to see very clear differences. Here we see again that downward motion that's associated with this cooling, but their downward motion is not as prominent. And the other thing that we saw was this upward motion just radially inside, radially inward of the complex here. So we wanted to investigate what's exactly happening here. And we did that by looking at the cross sections. And so we're focusing on this downwind cross section where they did the same thing, Moon and Nolan, and they showed that you have this mid-level inflow that descends, and also we have acceleration of the tangential wind given by the colors here and the colors here. So we have the local acceleration of the tangential wind and this mid-level inflow that descends and continues as radial inflow, and some radial outflow in the mid-levels as well on the other side of the heating structure. We were able to simulate something very similar, mid-level inflow that descends, but there were a few differences here that were notable. This descending inflow, of course, looked very similar to, or this descending inflow is something that was pretty noticeable. But other thing that we saw was this updraft that was occurring. We saw this in this plan view, and you can see it very clearly here, radially inside of this stratiform structure. And this is a forced updraft that is pretty prominent. You can see across the rainband complex that we forced here. And it, of course, looked very similar to what we saw in Hurricane Earl, where we have our mesoscale descending inflow in the stratiform region and a convective updraft just radially inside. So we wanted to make sure we fully understood the physics of what's happening. So we looked at an omega equation that's similar to the quasi-geostrophic omega equation, but it's based on the balanced assumption for a tropical cyclone, suitable for a tropical cyclone. And what we focused on was this buoyancy advection term, and this would be the vorticity tendency term, or the differential vorticity term here. And we have the vertical velocity zooming in on this rainband region from WRF. And we also have here the vertical velocity just from the buoyancy advection term. And you can see it looks very similar to what the actual vertical velocity was. So that told us that the vertical velocity that we saw was largely explained by buoyancy advection. And you can also see that clearly in the azimuthal gradient of the background, the anomalous temperature perturbation. So here we have a warmer air that's pretty much going right into more cool air, which is of course associated with the negative buoyant air that is sinking in the stratiform region. So this buoyancy advection is pretty critical for forcing that updraft. And the other thing that was pretty critical that Moon and Nolan didn't quite capture was that if you have this cooling region and you have it rotating around the storm, it creates a much different pattern if you just make the rainband region stay at one location. So instead of having this rainband region rotate around the storm, we had it parked in one location. And you can see very clearly that this updraft region, this is more associated with the eyewall. The updraft region associated with this rainband complex, a simulated rainband complex, becomes more consolidated. And this is a mimicking of the stationary rainband complex that past observational studies have been highlighting. And so this is showing us that when we have this stationary band complex, we have cooling in the stratiform region that creates this low-level temperature perturbation and gradient. And so through cold pool dynamics, this moist, warmer air reaches this cold pool and helps to force this updraft in the downwind stratiform region. if we connect this study to what we've seen in observations. So this helped us pin down what we think are the most important dynamics for this forced updraft. Now, when we look at this forced updraft in this simulation, it didn't go too far high. But if you recall, we didn't have any moisture here, or nothing was happening in terms of convection-wise in this simulation. So we know if we have a real storm, that forced updraft can easily create buoyant convection. And so that was our hypothesis, was that this is actually something that can trigger a pretty persistent region of forced updraft, or a buoyant convection. Buoyant updrafts, that's what I want to say. All right, so we've done the observations, we've done the idealized model work. Now I'll show some of our work from a real case simulation of Hurricane Matthew. So this is from a recent paper. I think it's in early online release right now. So we were able to do a simulation with a 1 kilometer horizontal grid spacing. It was convection permitting. We had WSM6 microphysics, and we initialized it using the Penn State Whorfian KF system, which included all of the available conventional observations, as well as the airborne Doppler radar observations that the P3 collected prior to the rapid intensification that Matthew experienced just before the simulation started. So this is just comparing the observed track and the WRF track, and this is the time in which Matthew experienced an eyewall replacement cycle. It's first, actually. We had another one, of course, by Florida. All right, so our simulation went, the focus time that we're looking at is from 0 to 36 hours here. And you can see this is a Hofmahler diagram of vertical velocity, and we can see this eyewall upward motion pretty persistent through time up until 25 hours. And at about 15 hours is when you can see a lot of a clear axisymmetric signal of rainband updrafts that propagate inward and eventually become the secondary eyewall that replaces the initial primary eyewall of Matthew. And now hours 15, 17, and 19 are shown by this black dashed line. And here is the layer average reflectivity with the shear vector. You can see just the evolution of this rainband complex. It grew over time, and by hour 21, you start to see hours 21 and 22, you start to see an axisymmetrization of a secondary ring of reflectivity, and this is where we have our secondary eyewall that becomes pretty prominent and eventually replaces the inner eyewall. Yeah, and the other thing is that this rainband complex was clearly aligned with the shear vector in the way that we expected, where you have more convective regions to the right and more stratiform regions to the left of shear. And you'll get to see all of the actual regime of the convective versus stratiform more closely as we step through. So I was excited to go into very extreme detail of this simulation. We of course had to balance the detail in which we looked at simulation with. I always tell my students, like, I love looking at observations and going into extreme detail of them, but with models you just have way too much data to go into complete extreme detail. But I was excited to approach this from somewhat of a quasi dual Doppler observation point of view, but with all of the data. So what we did was we focused, we looked at hours 15, 17, and 19. And here we have cross sections of the tangential wind acceleration at these times. And here we have the plan view with the quadrant averages. And so what you can see outside of 60 kilometers radius is acceleration at hour 17 that indicated the broadening of the wind field even up to hour 19. And you also see this acceleration in the low levels, which it was actually became more intense over time and showed the beginnings of the secondary eyewall. Now, from a plan view, you can see that this acceleration becomes very prominent in the downstream right and downstream left quadrants by hour 17. And here again, we see at hour 19 this acceleration band here that starts to become more circular, showing more axisymmetrization of this tangential wind maximum that eventually occurred. All right, so I wanted to focus on one of these hours first to show what the basic dynamics are in both the downstream right and the downstream left quadrants. I think I'm just showing downstream left quadrants here, which is where we would find, of course, our stratiform region of the rainband complex. So we calculated a quadrant average tangential wind budget. And here's the equation that we used for this. And we focused on, again, a quadrant average in the downstream left. And we looked at our actual change in tangential wind, and we did the integrated tangential wind from our budget terms here. And so that we can compare what our calculations were with what the actual delta V was. And patterns look pretty similar. And one of the things that we focused on was this descending inflow pattern of this tangential wind acceleration that looked very similar to the axisymmetric tangential wind acceleration. Now, when we broke this down into the different terms that were contributing to it, we focus on the horizontal advection. We saw that the horizontal advection, which is the azimuthal versus plus the radial advection, you can see that this pattern seemed to be pretty important pretty important in forming the shape of our full dVdt here. And this is again a descending in a descending pattern that showed azimuthal advection in the mid to upper levels, which was advecting these higher angular momentum air from upwind into this region. And this actually helped to descend, this actually transitioned into the lower level pattern where we have radial advection that became more important, drawing the angular momentum downward and inward. And so these two terms tended to be most important for shaping this pattern in this quadrant, which looked very similar to the overall axisymmetric pattern. Now, this local acceleration was, of course, due to mesoscale descending inflow that we saw in the data within the stratiform region. So we're showing the actual tangential wind consequence of this NDI that was persistent over time and also over space. Now, the other thing we were able to look at is seeing how this actually connected to how this mesoscale descending inflow connected to the diabatic cooling. But one thing I had noticed when I was looking at a lot of the observations is that I saw what I call ghosts of an MDI, particularly in these quadrants of the storm, where they weren't necessarily inflow, they were all outflow, so I couldn't call them an inflow pattern, but they had the shape of a descending inflow where you had a lower regions of outflow. And it turns out that we could actually capture what's happening when we look at when we decompose the winds into a non-divergent and irrotational components. And so when we decompose the winds and focus just on the irrotational radial wind, which is in the shading here, and we have it overlaid in the contours, we have it overlaid of diabatic heating and cooling. So when we have our irrotational radial wind, what we see is this stratiform, I'm sorry, let's focus on the contours first. Here in this region, this is the downstream left at hour 17. We have diabatic cooling that's happening just above diabatic heating, and this is a pretty clear stratiform signal between 60 and 80 kilometers radius. Now we also have a mid-level rotational inflow that forms just outside this region, and it of course passes through this cooling region just as we saw, just as we would expect from our idealized study and also from our previous observational studies. And so this would be the MDI that we saw in the downstream left quadrant. And it wasn't just in the downstream left quadrant where we saw this. We also saw it at later times, hour 19, in the upstream left quadrant. So this mesoscale descending inflow, which you can't really see in the, if you looked at the full radial wind at hour 19, you have to look at the irrotational radial wind, because that's the component of the wind that is the most important for creating the convergence in field response. That is a response of the heating field. And so this descending inflow in the irrotational sense was also present in the upshear left, where we also saw an extension of the rainband complex downwind. And the other thing that we saw was, of course, on the inner side was our updraft, and that also creating all this deep heating at both of these times. So this was a pretty cool finding, where we saw that this stratiform region again showed an MDI that helped force new convection. And this new convection actually helped to accelerate the local winds here. And this was connected to our secondary eyewall formation that eventually axisymmetrized. So how do we piece all these things together? So in this study, we were able to show this evolution over time and space in this Hofmahler diagram. So we have our shear relative azimuth here, and our simulation, and I was focusing again on hour 17 and 19. In the colors here, we have our average negative irrotational inflow. And the first thing you see is that this signal pops out at hour 17 in the downstream left quadrant. So this part of the storm is really important in creating this MDI. It's the only place that you see it at first. It's the first place you see it. And the other thing you can see is that it propagates downwind into the upshear left quadrant, just as we suspected from the plan views and the cross sections. And it's a descending pattern noted by this average. So the red contours here are the negative vertical velocity average at these radii. So this is a irrotational radial inflow that is descending, going from the downshear left to the upshear left. Now, if we connect that to what's happening with the tangential wind acceleration, so the first term here is always going to be the shading. So we can see that at the same time we have acceleration of the winds in the downstream left quadrant that's most prominent, and it gets to the downwind, and it's also driven largely by the acceleration due solely to this negative UCI, which is given here by the contours. And the other part of this is that just radially inward, we were able to see the acceleration that's occurring, also pretty strongly correlated to the vertical velocity. So at about hour 17, we have this red streak here, which is showing the local acceleration just radially inward, where we found our persistent updrafts. And that continues at different times, but they're all connected due to the fact that this is an MDI that's persistently going into the boundary layer. And it helps to trigger the updrafts, and which further contributes to the wind acceleration. Okay, so in conclusions, the current theories for secondary eyewall formation don't fully explain the role of asymmetric rainband convection. What I'm presenting here is a clear signal that we see that happens prior to eyewall replacement cycles or secondary eyewall formation, which is a mesoscale descending inflow that generally occurs in the downshear left quadrant. It's prominent in terms of time and space, and we've seen it in several cases, both observed and simulated. And I talk about this, the importance of this, because I think it's an important plausible pathway. Maybe several other pathways are possible. In fact, I would say that they are possible. But this seems to be a pretty plausible recurrent way for why we have the asymmetric rainbands that transition into a mature secondary eyewall. And this is just summarizing what I think is happening here. So in this cross-section, we have our mesoscale descending inflow in this large stratiform region where we have a lot of melting cooling, sublimational, and evaporative cooling that draws this in. And this sinks all the way down to the boundary layer, where if you have this cold pool that basically splashes into the high theta E boundary layer air, that helps to create this local persistent updraft in the downshear left quadrant and even into the upshear left quadrant. And how does this connect to the previous theories for secondary eyewall formation? Well, this persistent updraft over a large space gets to project strongly onto the axisymmetric mean. And it's not just an updraft, it's also a local wind anomaly, and it's also a local vorticity anomaly. And our previous theories need that asymmetric anomaly to project onto the axisymmetric sense to trigger axisymmetric dynamics. So that's definitely what I think is happening. The observations and the model simulation show that results that are consistent with this pathway for secondary eyewall formation. Now, this work and future work for looking into these asymmetric dynamics and interactions with the environment are pretty essential for better improving our understanding of eyewall replacement cycles and also forecasting them. Still a difficult problem, but I hope that this helps to bring more shed light on what's happening here. So I will stop there. Okay.
Virtual applause if you. We'll open it up. Question.
For not having applause. This is my first seminar digitally, so.
Okay. Questions from students first.
Do I click on this or? Okay. Is there a chat? Should I have been monitoring the chat too?
Oh, but you can click on that.
Okay. Hi, Ian. How does this work?
Hey, how's it going?
Hi, all right.
Good, thanks for the talk, very interesting. I just wanted to clarify something. I think that you showed it in your last, that conceptual diagram, just for myself, for my own understanding. So the idea is that the MDI is irrotational flow, and it's being advected around the storm due to the presence of strong rotational flow.
Yeah. So the MDI, in our observations, we of course couldn't call it irrotational flow, just because we couldn't calculate that. But in the models, it definitely seemed to be very clearly an irrotational element, and it's advected downwind. Just because we have that strong azimuthal advection that, and it's growing over time as well.
Cool. Okay, and then also, I'm just inquiring, so the idea also in this diagram is that the inflow in that cold pool is starting to force the new convection, and the idea is that that cold pool can no longer make it to the inner eyewall anymore, and so the secondary eyewall is just going to end up being the new center of convection while the other one will die out.
Yeah, so it definitely does reduce the, I wouldn't say it doesn't make it to the inner eyewall, just because it does help to reduce the theta E generally of the underlying inflow that's still going underneath here. but it does, because it is a cold pool, it does help to force some new convection. And the key here is that this is a different convective process in the sense that it's largely driven by cold pool dynamics than if we were to look at the other side of the rainband complex, where over here we don't have the same extent of the cold pool dynamics, and so you have pockets of updrafts that are associated with these sails, whereas over here this would be an MDI that is extending in the mesoscale over maybe 2 quadrants. And so that means that the corresponding new persistent updrafts would also be of that same scale or comparable scale.
Cool. Thank you very much.
Okay. Other questions? Well, while people are, we see a question from Lee. Do you want to?
So I saw one question. It said, what determines, oh, I see applause. Thank you. I'm kidding. What determines the location of secondary eyewall formation? That is a great question. That is still not completely determined. If it is this process, if this is the primary, the most frequent occurrent process, it would have everything to do with the initial wind field, the initial extent of the rainband complex. You definitely need to also take into account the environmental moisture to see just how cold of a cold pool you can create. But I think in general, that's another issue is, could this NDI process occur if a rainband complex were even closer to the inner eyewall? We do see some rainband complexes that merge right into the inner eyewall, and that would create a secondary eyewall that, or the initial location of a secondary eyewall to be very close, but you can't have it too close because the inner eyewall would tend to it could disturb the outer eyewall development. So it's definitely something that's still in need of more attention.
Additional questions?
Hi, this is Noor here.
Hi.
So just following on the question that I asked, is it why we saw there's only like medium strength hurricanes, which are Cat 3 to Cat 4 hurricanes that formed the secondary eyewall, and not the weaker storms because they don't have enough inflow to advance the I guess evaporative cooling into the right location?
Yeah, that's a complicated question. I do think, of course, that with your stronger storms, you definitely have a more organized rainband complex, and you also have a larger contribution of your acceleration. Of course, the stronger the storm, the more you can accelerate this outer flow. I don't remember which one I was looking for here. Yeah, that's a complicated question because but it also depends on what we're calling an eyewall replacement cycle or secondary eyewall formation. I am starting to notice more clearly that even weaker storms can have what can be called a secondary eyewall. It's just not as prominent or good looking as a stronger storm would have. But I think the larger that is definitely one aspect is this downwind this downwind advection and axisymmetrization is definitely more efficient with a stronger storm. Yeah, Derek.
Hey, Anthony, that was great.
Hey.
And kind of playing off of that a little bit, and I think you just kind of answered a little bit of my question, is that you're kind of showing this kind of ideal ERC evolution, but the truth is that ERCs tend to fall kind of on a spectrum of very clean ERCs that are very obvious with a well-defined moat, and other ERCs that are much harder to discern. I'm putting together ERC databases, and when you look at these cases, from a subjective sense, it's sometimes difficult to tell if an ERC is actually occurring. And I think one of the things I want to get at here is that there appear to be these ERCs that occur early in the process during the intensification phase that seem to be somewhat different structurally than this process that you're showing. And I wondered if you had looked at any of those earlier cases and if it fit this kind of model that you're looking at here.
Yeah, so the answer to your question is no, I haven't looked too closely at weaker storms. Let me bring this up here. Even here with Earl, Earl was, I think, a Cat 1 at this point. There was some stronger winds at 25 kilometers radius, and I would say that this was an eyewall replacement cycle just like prior to its RI that occurred. And so I think this is an example that I probably could look more closely at to see if it's what we can call a secondary eyewall and eyewall replacement cycle for a weaker storm. So yeah, I have not looked. I think that that's an important thing to look at, and I haven't looked at it in depth. I'm curious to know what you are thinking of or seeing when you say that the structure isn't the same. So I'm curious to know what you're.
Yeah, well, our primary motivation here is an intensity change. So these early events don't seem to impact the intensity as much. They may abate the intensification process for a short period of time, unlike the classic ERC where you have an actual replacement of the inner eye wall, which tends to promote at least some weakening in the storm. So.
Okay.
Yeah,
Okay.
I think kind of comparing some notes and maybe sharing some examples of some of the cases we're looking at might be helpful there.
Yeah, sure. Yeah, let's do that.
Yeah, and if I could just follow up real quick, you talk about wind field expansion seems to lead the convective structure. Is that correct?
Well, I was trying to be careful not to exactly say that. So I do think that that's one of those chicken and egg problems where it's not quite clear if the rainband convective structures or rainband convection is it definitely is accelerating the local winds, but are the accelerated local winds something that also happened prior to the enhanced convection that helped to create the convection itself? Because that's another definitely can create more convection through different processes.
Okay, yeah. Thanks for saying that, because that was very interesting. As we look at clues in satellite imagery, for example, to determine when these processes are going to get underway, we're primarily looking, when we don't have radar, like you do here in many of these cases, we're looking at satellites, especially microwaves. So, yeah.
Cool. Thanks.
A quick question for you. Actually, one is the process going on the
Michael, you're breaking up.
Okay, maybe I'll type this out. I'll type. Well,
this is a cool feature here.
Yeah. Any other questions from anyone else while Michael's typing his up? We will patiently wait.
Can eyewall replacement be viewed as a continuous process? What do you mean by continuous process? Well, there are definitely different flavors of eyewall replacement always occurring, and something triggers the formation of a dominant one.
so if I'm not breaking up,
Yeah, I can hear you.
occurring, and then at some point something clean occurs that allows a second one to actually form. So what may be fundamental? What triggers the formation of if these processes are occurring?
Yeah, that's a great question. Like, why like these rain bands are always happening here. Why would one storm, are you asking why would one storm that has rain bands be different from another if one creates a secondary eyewall and the other doesn't? Okay. Yeah, that's a very good question too. I think that it's very much, again, well, just from, it is a two-way street in terms of the wind field expansion and the convection. Some of the recent work that I've been seeing suggests that there can be other processes that help to expand a wind field even prior to more directly than the actual convection itself. So so that's more tied to the environmental wind profile. Other aspects could include different sea surface temperatures or distribution, and also the environmental moisture. So these are things that I think can play a role in differentiating between which complex is going to help drive the one that is most important. And it's definitely an active area of research. I know I'm going down the rabbit hole with that from an observational point of view now. Diurnal fluctuations as well. Yeah, that's important. I was having a good chat with Michael about that earlier. When you have fluctuations in the convection throughout the storm, just due to diurnal cycle, and that can help trigger diurnal pulses, basically. And if those align well and with the timing of with the pre-existing convection, then that can play a role.
Thank you. And then one final question.
Yeah.
The moon.
Sorry. Can you start over, Michael?
Just the Moon and Nolan work and the work you and your student did with the idealized example. My question is the dipole heating above cooling.
Mm-hmm.
That's going to lead to a potential
mm-hmm. Yep.
intensification of the area eye wall in terms of convection around the vortex.
So you kind of broke up there, but it sounds like you want to talk about the PV that is generated in the stratiform region in the mid-levels? That's
correct, and how it relates to the spin up of the secondary eye wall and its subsequent.
Yeah, so that's a good question too. That PV generation is very much tied to what we see in with the mid-level tangential wind jet. And if that is the same, if that is the tracking the newly formed PV, one thing that we see though is that this newly formed tangential wind jet that's on the mesoscale, it doesn't quite always axisymmetrize around. It's not the main way in which you have that axisymmetrization happening. So yes, there is PV that is generated, and some theories or some studies suggest that can spiral into the storm core itself and help to improve the PV core of the storm. But in terms of the PV axisymmetrization that is created for secondary eyewall, in the studies that I've been working on, it has more to do with the updrafts, the convective updrafts that are axisymmetricizing. And that's a more efficient source of PV generation.
Thank you.
All right.
Other questions? Well, thank you, Professor, for wonderful talk, answering the questions, being responsive. You had a great visit, and hope to base here at some point.
Yeah, thank you for having me. Thank you all for coming out.
Thanks, Anthony.
All right, I think that was John. Thank you.
Yeah, thanks, Anthony. Great talk.
Hey, Angel. All right, I guess I'm done. All right, take care, everyone. I guess I can.
Put sharing your screen and get out of here, right?
Okay, how do I do that?
Hang on, I'll stop the recording.